Alright, subscribers, welcome back to another episode of Science with Surback. Today, what we're going to be talking about is section 16.3 in Intro to Chem and Physics. And what this is really a continuation of talking about light waves. We can talk a lot more detail and get into a lot more depth in this section and actually the last section too as well. But section 16.3, I got a couple of objectives for you to be able to meet by the end of this video. Objective number 1 is determine how objects interact with incoming light. Objective number 2 is determine how you can see an image in a mirror. And then the third and final objective is to understand why we see color. So we first have to start out here with some basic concepts of light reflection. Number one thing here is that all objects reflect and absorb some light. The second thing is that the surface of the object is going to determine the way light is reflected. And to get you to the mindset of light's reflection, let's think of a simple example such as looking at yourself in the mirror. So when you look at yourself in the mirror, what's happening is the reflected light that you are seeing allows you to see an image of yourself. And that is true. If I show you this picture here, this is a man standing in front of a mirror, and because of the light's reflection, he's able to see an image of himself. So now that we have some basic principles of light's reflection, we can now turn our attention to a concept known as light waves. Now, light waves are defined as a line in space that matches the direction of the flow of radiant energy. And so what it's really saying is this is another model used to describe light. Now we have to remember that light rays are going to move in the same direction as in the wave model of light and as the path of photons in that particle model of light. So if the light ray is just another model and it's describing light similar to that of the wave model and that of the particle model, well, why is it used? And we have three different uses for this light ray model. Number one, it describes reflection. Number two, it describes refraction. And number three, it's going to describe the behavior of light. Just like the wave model and particle model described how light behaved, the ray model here extends that explanation. It gives us a little further detail into how light is behaving. So that brings us down here to this term known as a geometrical optics. Now, this is just the study of light using the light ray model of light. Now, what it's going to do, it's going to use geometric drawings called ray diagrams that display the path of light rays. Now, to give you an idea of what these ray diagrams look like, I have a picture here that is a ray diagram. You can see that the ray of light is simulated from this particular light source, the flashlight, and the arrows indicate the direction of travel of that light ray, and that is the ray diagram. Now, it unfortunately does not give a full picture of the Again, it's important here that we have this light ray model of light, but it doesn't give a full picture, and that's why we have to use multiple models to describe the true behavior of light. So, before we can get into any more detail about light and light reflection, we have to go over some terms associated with the reflection of light. So our first term that we have here with our reflection of light is the angle of reflection. And it is defined as the angle of the light rays reflecting off of a smooth surface. Now, to show you what the angle of reflection is, I have this picture right here, and it's really similar to the one I showed you earlier. And so the angle of reflection, again, the light's coming down here, reflecting off a flat mirror, and then shooting back up and towards the right. Now that angle right here on the right is the angle of reflection. Now, on the flip side, over here on the left is the angle of incidence. And now the angle of incidence is just defined as the angle light rays strike a smooth surface. And so that brings us down to the term of the law of reflection. And now the law of reflection is going to state that the angle of reflection is equal to the angle of incidence. And so if we turn our attention back to that picture I showed you here, we have this. If you look really closely here, you'll see that the angle of incidence coming in here from the left is equal to the angle of reflection. Now, this middle line here bisects that particular angle of incidence and angle of reflection. And you can see here, these signs indicate that we have an equal angle. Now, another thing here is this dotted line that bisects the angle of incident and reflection. Well, that dotted line is known as the normal, which is defined as the line in which the angle of reflection and incidence are measured from. So now that we have these four definitions, what we can do now is turn our attention onto a little bit more detail as to what happens when we reflect off of not just flat mirrored surfaces, but what happens if it's not flat, which is a lot more common. So the next thing that we do is we look at both of those things here. So by having the light being reflected off different types of surfaces, we get a little bit different behavior from those light rays. So we start out here with light being reflected off of just smooth surface, like that flat mirror. And so with a smooth surface, light is going to reflect into a single new direction. And so if we take a look back at the picture we've been looking at, it's going to look, the light rays at least, are going to look like this bottom picture where we have the light rays coming in, and then we have the angle of reflection with this nice, smooth, clean-cut angle. So just as a reminder here, our picture is going to be this. We have the light ray coming in, it reflects off the surface, and it bounces into a single new one direction. Now, light being reflected off a rough surface. You probably saw the picture just above what I just showed you. And so light that's reflected off rough surface is going to reflect in random directions. And that looks like this top picture here, where the light rays come in, they strike that rough surface, and you can see that the angle of reflection here is every which way. It's not a single new direction. And we call this specifically a diffuse reflection. And so just as a reminder here, we're going to draw that picture as well. We're going to have this light ray come in. It's going to reflect off a rough surface, and it's going to go in many different directions. It's going to have a diffuse reflection. Now, I like to have a couple examples to think of what surfaces may be considered rough. The first example that I have is light being reflected off of an object like wood. The second example I have is light being reflected off an object like cloth. And then that third example I have is light being reflected off of an object like skin, the skin on humans. So now that we have some basic terminology and some basic understanding of how light is reflected, we can shift specifically to mirrors, and we can talk about how mirrors, what they do when light is reflected off them. So first things first here is we have some basic principles that we need to discuss about mirrors. Number one, the law of reflection is going to describe the light reflected by mirrors. So remember, the law of reflection stated that the angle of incidence is equal to the angle of reflection. And that's for those flat mirrors. Now, something to keep in mind is that light reflected by mirrors that actually reaches your eyes is an image of what is being reflected. So the best way to think about the basics of mirrors is, once again, going back to this picture here, and you see that the man standing in the mirror, and what he sees is that image. That's that reflected image that his brain is going to pick up. Now, I have a flat mirror here, and if I hold it under the camera, you can see that there is a reflected image of my ceiling. And if I turn it towards me, you can start to see my reflection as an image in the camera there. So that's the basics of how a mirror is going to work. Now, specifically with our mirrors, we have two different types. We have two different types of mirrors, images that are reflected via mirrors. The first of these images that are reflected is a virtual image. And I'm not going to get into a whole lot of details here because I dedicate a whole page talking about virtual images and how these images are produced. The other type of image is a real image. And so, distinguishing between real and virtual, the actual type of image that appears is going to depend on the type of mirror that is used. And in the next page, we'll talk about different types of mirrors. So far, we've only talked about a flat mirror. So the best way to go through this is breaking down that picture I've been showing you, and that's seeing yourself in a flat mirror. Again, I reference this picture right here as what we're going to be talking about. Now, the best way to think about this is to step into your bathroom and look at yourself in the mirror and think about these principles that I'm going to talk about here. So the first thing here is that a copy or twin image of yourself is seen on the other side. And this is shown right here. And this twin image on the other side is on the other side of the glass mirror. So what you're actually seeing is an image, and it's going to be a little bit different than what's actually there. And that will make a little more sense when we distinguish between real and virtual images. The other thing is that the space behind you is seen. And again, the best way to see this is actually go in your bathroom mirror and look closely at that image being reflected. You'll see that space behind you is also reflected. And then you have to keep in mind that the angle of incidence is also equal to the angle of reflection. And then the fourth point here is that the image that you see in a mirror is actually flipped from left to right. And this is best explained when you hop in front of that mirror and you put up your left or right arm and you start moving that arm. You can start to understand what I'm pointing out here in this example. So now that we have this basic understanding of mirrors, we can get into the specific type of mirrors and we can distinguish these different types. So we've talked in depth and in detail about these flat mirrors, and now we need to talk about curved mirrors. What if that face of that mirror isn't perfectly flat? So curved mirrors are going to cause light to be reflected in different directions because the line perpendicular to the mirror, quote unquote the normal, points in different directions. So we'll draw ray diagrams here in a little bit, but the light that's reflected, again, is going to point in different directions. Now, because this happens, because the lines reflected is going to point in different directions, it's going to distort images so they are smaller or larger than real objects. So we have two different types of mirror, a convex and then a concave mirror. If we start out here talking about a convex mirror, this is a curved mirror that bulges outward. And so it looks like this. You can't see it probably very well on the screen, but it does have a bulging outward appearance there, and it's going to make objects appear smaller than they actually are. So if we can get a pencil, the same pencil that I have been writing with, you can see on the screen that this is the size of the pencil. And if I bring my pencil up to the mirror, you can see that the reflected image in that particular mirror is significantly smaller. I almost have the pencil right up against the mirror, and you can see the image, because of the curved mirror, is actually in fact smaller. A good example, a good real-world example here, is going to be the passenger side mirror in a car. It's actually a convex mirror. So on the flip side, we have a concave mirror. And so a concave mirror is going to have a curved mirror that is indented inward or pushed in. Now, again, I have an example of a concave mirror, and it's hard to see the indent in, but maybe you can start to see that the objects actually in this particular mirror are actually going to be magnified to make the object larger than they actually are. So if we can try to take my same pencil that I've been writing with, and I showed you in the convex mirror, and I take the concave mirror, and let me try to match it up here with the lens of the camera. And what I'm going to do is this. Oh, perfect. All right, so check that out. I'm holding the pencil about the same distance away as I did with the convex mirror, and look how much larger the pencil of the image reflected by the mirror is compared to the actual pencil. It's significantly larger, and that's what a concave mirror is going to do. Now, a specific example of a concave mirror is or are mirrors that are used in reflecting telescopes. So remember, those telescopes that are used to see objects in space are trying to magnify objects that are really, really far away. So they need to be able to magnify the size of that object. So we now have a basic understanding of the three different types of mirrors, the flat, convex, and concave mirrors. Now we can get back to that business we talked about earlier with a real and virtual image. So we start out here with this business on virtual images. And virtual images are just defined as an image from which light rays appear to diverge even though they are not actually focused there. So the best way to see or talk about virtual images here is from the actual ray diagrams of a concave and a convex mirror. So I'm going to pause and draw those, and then I'll resume and we'll talk about them. So these virtual images are produced when we have our light rays start to diverge. So in our concave mirror, the diverging of these light rays occurs right over here. So it's been bounced off or reflected off of the mirror, and then as these light rays spread away from each other, that's when that virtual image is produced. Now with a convex mirror, the focal point is actually behind the mirror, and that's part of the reason why it makes that object appear smaller. But with a convex mirror, after we hit the focal point behind the mirror and these light rays start to diverge from one another, again, that's when that virtual image is produced. Now, one thing with virtual images is that they cannot be projected onto a screen. And the reason that these virtual images cannot be projected onto a screen is because of these diverging rays. Unless you're at the focal point, you can't make out that image. It's going to be blurry and distorted, and it's unable to be seen on that screen. Now, the best way to think about this virtual image is, again, that example of seeing yourself in a flat mirror. So what is happening is this: when you actually see yourself in a flat mirror, and like I said, the best way is to go in the bathroom, turn on the light, and just literally watch yourself in the mirror, and you'll understand this a little bit more in depth. But what's happening is that the light from the mirror is reflecting and reaching your eyes in all directions. Now, as this light reaches your eyes in all directions, what the brain is going to do is it's going to interpret the light as if it traveled in straight lines from an object, that mirror, to your eyes. And so what the brain does is it perceives an image of yourself actually behind the mirror. And so if we take a look about this picture once again, we see this. We see this little faded point here, and that is the virtual image produced by the brain, how the brain takes those light waves and pretends that, hey, they're all coming in a straight single line, where in reality, they're actually coming all over. They're coming in every which direction. You see all the rays that are coming at all those different angles. The brain says, hey, I'm going to take it in as one angle and then produce that image. Now, what happens here ultimately is that the virtual image of your reflection appears to be far behind the mirror as you are in front of the mirror. So if I emphasize that one more time here, the virtual image here, you are going to appear behind the mirror. And that's why it is a virtual image that is produced. So now that we have an understanding of these virtual images, we can shift gears and we can start talking about the term of real images here. So as we shift gears here, we'll do something similar to what we did for virtual image, but obviously a little bit different content here for that of real images. So with real images, they are going to be defined as an image that is formed by the intersection of light rays. So again, the best way to see this is through those light rays that we just drew. So I'm going to pause again, draw those light rays, and then we're going to talk a little bit more about that. So there are the ray diagrams from our two mirrors again, and we have an important point we have to make here. The focal point is very important because the focal point is actually the point of the real image. So for a concave mirror, the focal point is going to bounce. They're all going to intersect back into that field, and that is the point of the real image. Now, for a convex mirror, the focal point is going to be behind the mirrors, and again, that focal point is going to serve as the point for a real image. So now with this objects here, we can understand that at the focal point, that object is going to come in focus, and these particular objects reflected by or through a real image can be projected onto a screen. Another couple important points to make here with real images is this. A real image appears when those light rays come together. So again, that focal point is where all those light rays come together at. Now, on the flip side here, a virtual image appears to exist in certain places, but no light rays exist there. So, one additional point, and I should have made this when we were talking about a real image. A real image can also be said to where light rays exist at the point the real image appears. So almost that focus point. And that's why with real images it can be projected, because if you ever used a projector and you've hooked it up to your computer, initially that projected image is really blurry. And so what you have to do is you have to adjust the focus so where those light rays come together, it focuses it on that projection screen. Our final thing here is just an example of a real image, and that's the image seen from a movie projector or a computer screen projector that takes and it focuses it, and that focus point is that point that the real image can be seen. Alright, so now what we can do is we can shift gears and go from images and light rays from mirrors to talking about color. So when we see color, when we go through this process and we see color, what is happening here is that the colors we perceive, or that we actually see, is going to depend on the wavelengths of visible light that actually reaches our eyes. So the best way to understand this business about wavelengths and color is to actually go through an example. And in our example, what I have here is a picture of a rose, and what we are going to focus on is that red color from the actual flower petal. Now, what happened here is that light that strikes the flower of the rose is going to reflect light with a wavelength of about 700 nanometers. So that red that we see is from a wavelength of about 700 nanometers. Now, the wavelength of 700 nanometers is what our brain picks up as the color red. Now, the flower petal is going to absorb all other visible wavelengths and does not reflect them. So, to put this all together, the reflected wavelength of 700 nanometers is the light wave that enters your eyes and is what your brain interprets as the color red. So, what we have here is this. We see the color red in this rose petal because that light that reached our eyes and eventually our brain interpreted it is about 700 nanometers in its wavelength, and that is corresponding to that red color. Now, we can just talk about the flip side, and we can talk about the leaves, the green parts of the rose. And so light that strikes the leaves of the flower is going to reflect light with a wavelength of about 550 nanometers. The wavelength that has a 550 nanometer wavelength is going to be the color green. Now, these leaves are going to absorb all other wavelengths and does not reflect them. So that's what everything is shown here. You can see they have the whole visible spectrum, and then the leaves absorb all of those wavelengths, or those colors of those wavelengths, and then it just reflects the wavelength of 550 nanometers, which is this green color that actually enters your mind. Your eyes interpret and your brain interprets 550 nanometers as the color green. So that's the simplistic way of how we see color. Now what we can do is we can look at color through some filters. And with these filters, I'm not talking about Snapchat or Instagram or TikTok filters. What I'm talking about is I'm talking about a clear, transparent filter that has a different color. And so what these filters do is they transmit the light of the particular colored transparent filter and absorbs all other colors of light. And so to give you an idea of these colored filters, I actually have these filters here, and again, you can just see that they, if I hold it up to the camera, they are clear and transparent, but they do have a specific color associated with that. So I have 5 different ones, and we'll talk about here a little bit more in depth and more detail about these particular colored filters. So the best example that we have is this. We're going to view that same rose petal or that same rose flower now through a colored transparent filter. And this is that picture that we're going to get when we view the rose flower through a red colored transparent filter. So if we take a look back at this picture here, what happens is that the red light is transmitted through the filter and all other light is absorbed. And so what specifically happens then is that if we take a look at this picture, the rose petals on the rose flower will appear red, and then all other parts of the flower will appear black, or that dark color you can see from the leaves. I know I squeezed this in here, but the last part says rose petals on the rose flower will appear red and all other parts of the flower will appear black. So what we can talk about is how the white light of sunlight passes through a prism. Now, I don't have a great example of this, but I do have a picture of what I am talking about here. So with our picture here, we have this. This prism is this clear object that is going to separate white light from sunlight or another source into its individual wavelengths. Now, one thing here is that what happens is that when white light, or sunlight for that matter, enters into a prism, it is going to separate into the colors of the rainbow, which means we have all of the visible spectrum present in that white light. So this white light, again, I mentioned it several times in this picture, or this portion here. The white light, actually sunlight, is going to contain all the wavelengths of the visible light from the electromagnetic spectrum. So if sunlight passes through a prism, we're going to see a rainbow. We're going to see all the colors of that visible spectrum. So our final part that we're going to talk about in notes is what happens when we mix different colors of light. Now, the key word here as we transition, the key word here is mixing light. I know some of you might have a background in art, but we have to keep in mind here that we are dealing with light and not art. So the first thing here is this. Most colors seen from light are not pure color. So what that top statement means is that most of the time when we see color, it's a mix from different types of lights or different colors of lights. So let's talk about what happens when we mix primary colors of light. And the first thing that I need to mention here is that the primary colors of light, or what we call the additive colors of light, are red, green, and blue. And when we mix two of those additive colors together, so either red and green, red and blue, green and blue, when we mix those together, we get three unique colors. Mixing red and green gives us yellow. Mixing red and blue gives us magenta. And then mixing green and blue gives us this. These three colors, yellow, magenta, and cyan, are known as secondary or subtractive colors. Now, you may have seen from the picture, but if we mix all three primary colors together, so red, green, and blue, and we mix them evenly, we produce the color of light that is known as the color white. Now, if we mix these subtractive colors of light together, so if we mix yellow, magenta, and cyan together, we get a new type of light to be produced. So again, just as a reminder, the subtractive colors of light are yellow, cyan, and magenta. If we mix these three colors of light together, what happens, or we mix two of those together, what happens is this. Whoop, got the wrong picture. What happens is this. If we mix yellow and magenta, we produce red. If we mix magenta and cyan, we get blue. And if we mix yellow and cyan, we get green. So we go back to those original or those primary colors when we mix two of those subtractive colors together. Now, you may have seen that if we mix all three subtractive colors together, we produce black. Now, black is not a color of light, it's actually the absence of color. So again, all three subtractive colors mixed together of light produces this black. Now, in light, there is no color black, and that is because when we get a black to appear in our color for light, this means that number one, all light has been absorbed. And so this black that we see is actually just the absence of color, and that is the color of light. Again, a little bit different than what you would have in art class. All right, so this is the final part of section 16.3. I hope you have enjoyed this video, and as always, remember to subscribe.